So in this video, I'm going to explain least square regression by in this book called Neural Network and Deep Learning. This is a resource for myself, and I never did this before, but teaching someone and teaching myself, and I can refer back to this some point. So let's go line by line, right? So in least square regression, training data consists of n different training pairs: x1, y1, uh, where xi is a d-dimensional represent and yi is a real value target. Basically, it's saying like a table, right? Uh, Give this. So basically, can I right click this? And okay, can't. So basically, there's like a table, and here's like x1, x2, xn, and this is like your y. This is your class label. This is the one that I'm trying to predict. These are all the features. So basically, it's saying y. So it's basically saying there are a lot of pairs x2 y and here should be like that. Such a bad handwriting. Xn comma y, right? That's basically the first line where yi is a real value target. So real value target is meaning it is basically a real number, so it can be like 1 2 1.5 whatever, right? So it is a real value. Y is a real value. The fact that the target is a real value is important because the underlying problem is then refers to regression rather than classification. So regression basically implies that the class label that you're trying to predict is a real number, and classification basically means that the class label that you're trying to predict is it's a class. It's like bucket, it's either 0 or 1. It's like this is classification. And regression basically is it can be 0 0.1 1 1.1, something like that, but it is in some range. You don't know exactly what range, but it is in some range. uh, how do I clear the eraser? Okay. Alright, the fact that target is important. Alright, least square regression is also gradient method. Okay, very closely related to some stuff. In fact, as later see on binary track is by pretending. Okay, so in fact, as you'll see, one of the least square regression on binary targets by pretending that these targets are real valued. So what he's basically saying is, you have a class label, which is basically either is going to be 0 or is going to be 1. All right, but this algorithm that you have is not a classification algorithm, it's a regression algorithm, meaning the algorithm is designed to predict not like these kind of class label, but like a range, right? So the class label is designed to predict the thing in a range, but the input you're giving is either 0 or 1, so it will predict either 0 or 1, but the design of the algorithm is used to predict real valued, and he's saying by pretending that these targets are real valued. The resulting approach is equivalent to Winder-Roe-Hoff learning algorithm, which is famous in neural network literature as second learning. Honestly, I don't care. uh, in least square regression, the target variable is related to features using the following relationship. So the target variable, so y hat. So when he writes y hat, uh, oh no, I just want to like erase this. I don't know how to clear canvas. Okay. So when he's saying y hat is basically the value. Uh, y hat is basically the value that the computer predicts. Y hat is basically the value the computer predicts. So here is saying y hat is equal to w dot xi, and w is like the weight vector. W is like a weight. It is like the constant, a b c that you see in an equation. Let's say you take y is equal to ax plus b x, where x1, where actually x is equal to 1. So This is just be like y is equal to ax plus b. Actually, weight is basically this a, b, these variables, not these. And you're predicting y. Y is the stuff that you're predicting, which is either is going to be 0 or 1 or a real number, whatever. And note the presence of circumflex. I didn't know what this meant. I thought this was some coding thing. No, it's just this hat thing. It's called circumflex. Whatever. Is indicated to predict. Is on top of y hat is indicated that it is a predicted value. Meaning, this is what the algorithm is predicting. The bias is missing in the relationship 2.5. Bias is basically this. Uh, Bias is basically like a neuron, which is you're basically letting like a constant be in the end plus c, where c could be any constant variable. So this is bias. That's what he's calling as bias. So in neural network, whatever this thing is, you are sending it right to whatever. This is like, here's like x1, x2, x3, so on, and here's your weight b, c, d. So this one is going to be 1, and this is going to be like bias. So usually people write it as b or whatever. I don't know, man, what people write, but this is what he means by a dummy feature, that is the bias. Throughout the section of the book, it will be assumed that one of the features in the training data has a constant value of 1, right? As a constant value of 1, this one, and the coefficient of this dummy feature is the bias. This is a standard feature engineering trick borrowed from, okay, it's a trick. And the neural network, the bias is often represented with the use of bias neuron with a constant output of 1. Yeah, so in a neural network, it is represented with the bias neuron, basically this, with a constant output of 1. So the output is 1, that's what you're seeing here. Although the bias neuron is almost always used in real settings, we avoid showing it explicitly through this book in order to maintain simplicity in presentation. So he's basically saying, I'm not going to talk about this, I'm just going to assume that this is always going to be there. You just need to be smart enough to remember this throughout the book. Gotcha. The error of prediction EI is given by EI is equal to yi minus y hat. So this guy, what he means by error, it took me some time to understand this, even though it's a simple thing. So you have your data that you write. You have that is like your oh my god, that is like y, and here's like all the x1, x2, x3. You have all this data, and you have y. What he's saying, and you're trying to like predict for a new data, for an unseen data, what would be a y, right? So this is like the y hat. So what he's basically trying to do, he's taking half of the data without knowing. He's considering this to be, oh, let's assume that the system never sees it. That's like the training, and he's like the test data set. And he's saying, okay, the error obviously is going to be what the actual value is, right, which is y, minus what the predicted value is. That's what he's saying here. What the actual value is minus what the predicted value is. Here, w bar is equal to w1 wt, the d-dimensional coefficient vector that needs to be learned so that to minimize the total error. So your goal basically is you're trying to find the appropriate weight such that the square of this error, so the y minus y hat square is minimum, is what he's saying. And y square, you ask, the way I think of it is like, it doesn't matter whether it's positive or negative. So when you're squaring it, the end result is going to be positive and it's going to be a bit amplified. So it doesn't matter. So small things can be like exaggerated. So you're trying to make sure that it is minimum. That is what he's saying here. Need to be minimized total training data set, which is the proportion of loss that is specified to the ith training data set in this instance is given by the following. So yeah, so loss so the loss function or whatever, so the loss, which is writing as L, is equal to E square, which is equal to y minus yi square. Got it. This is going to perceptron, except that the squared loss is paired with the identity activation function. This loss is simulated with the use of architecture similar to the perceptron, except the perceptron paired with an identity activation function. What is identity activation function? I don't know. Hmm. Oh, here's identity. Oh, so okay. S- So I think it's just gonna predict. Yeah. So the identity activation function is basically this. Now, what does this mean? How do I explain this? So, so the loss is going to be like on the on this. So the architecture is shown by below, whereas perceptron architecture is shown. Both perceptron and D-star has similar goal of minimizing and predicting error. So perceptron is a neuron which is basically older model, the first one that was created in neural network. Is first thing that was created in neural network is basically the same thing as least square, but it does with binary. So it's either 0 or 1, and that's the difference. This is like perceptron. Perceptron basically does between 0 and 1, and the stuff that least square goes for a range. Goes for a range. And let's read what loss function is. I'm curious now. In activation, it defines to the node given set of output the standard on or off depending on the its behavior. Oh, oh. So basically, the predicted output is going to be in this line somewhere. That's the loss function. I think it's going to be somewhere here in this line. So that's like it's like all numbers, I guess. Interesting. I don't know. I don't know exactly what loss function does, but I think that's what it does. Uh, the most common network, however, nonlinear networks, non-trivial approximation. So basically, I think it's approximating it to this value. So I think if some value comes here, you're just approximating it to here. You know what? I don't know exactly, but will both perceptron and least square have the same loss function, which is the identity one. I'll get to the loss function later. However, since the loss function in classification is inherently discrete, the perceptron algorithm uses a smooth approximation for the desired goal. This results in smooth perceptron creditation, which is seen below. So what is this figure? Let me check out. Oh, so here's like the difference, right? Which is basically there's x, which is like input. This probably would be like the bias one and weight. Here's your activation function, where you're like sending the input in this, and then you're getting your loss function, non-differentiable loss. This is like the perceptron, but with continuous output. This is sine activation, and this is like a linear activation, which is like that line. Oh, sine. I think no. The stuff has like sine activation. So perceptron creditation, smooth surrogate. So it's either minimum of 0, comma minus of this. I don't know what this is. Loss is something I still have to understand. Okay, eventually we will understand. Both minimizing role. However, since the loss function in classification is inherently discrete, perceptron algorithm uses smooth approximation of the desired goal. This results in smooth perceptron criteria shown in this. As we will see below, the gradient descent update in least square regression is very similar to that of perceptron, with the main difference being that the real valued errors are used in regression rather than the discrete errors drawn from +2, -2. So he's saying the biggest difference here is the perceptron is binary, and linear regression is in a range. As in the perceptron algorithm, the stochastic gradient descent steps are determined by the computer computing the generated computing the gradient of ei square with respect to w when the training pair xi, yi is presented to the neural network. stochastic gradient descent. Okay, when the training pair is presented by neural network, the gradient can be computed as, okay. So it's trying to find the gradient descent. Gradient descent is basically, uh, if you have like the error, you have to like get closer to the error. Less closer. Let's say this is a true shape, but let's say this is like the true curve, right? But this is the curve that you got, and this is like the error, right? You calculated the error, and this is the error. So what gradient descent, stochastic gradient descent basically does, it randomly picks up values, different values, and it calculates how much closer it should go, like this, and sometimes it goes like that, and then it goes back like this. So gradient descent basically tries to like course correct, right? That's why you see here w is equal to w plus alpha ei x, and this is like the original. Let's say this is a curve, so it's like this minus, based error will be like minus whatever, or plus, it depends. So let's say, oh my god, so crazy. Let's say this is a graph, right? And let's say this is the actual one, and this is the one we got. So you're saying this is like w is equal to w plus alpha e x, and based on your e, it will either go plus, so your w will update. Do you see it? W is equal to w plus, your w will update here. uh, but that's basically what this book is saying here. Therefore, the gradient distance updates w by computing the gradient distance by step size alpha. So step size alpha is, so the error, it just completely doesn't eliminate it, because then you're not then it overestimates or underestimates, and you're just doing it once, and it always jumps a lot. Let's say you have a big alpha, so let's say, and this is the good curve, and let's say you have a curve like this. If your error is big, then it'll jump like this, and once it's here, it'll jump like this, and once it's here, it'll jump like this. You'll never actually reach this one, which is a true one. So you like jump slowly. You jump slowly till you reach this one. This for computing gradient distance step size. One can rewrite the above as updates as follows. W is equal to, yeah, so E, right? W is equal to y minus y hat into x bar. It is possible to modify the gradient descent updates of least square regression to incorporate forgetting factors. Adding regularization is equivalent to penalizing the loss function of least square, with the additional term proportional to lambda dot w square, where, so to this you're adding a regularization parameter. So regularization parameter basically is a parameter that you add to this equation, so that it doesn't overfit the data. So you have a data, and let's say like you have like points here like this, right? Let's say you have points like this. You don't want the algorithm to like overfit, like, and make sure it's no, this is not the algorithm. You want an algorithm that's kind of like this, right? So what regularization will make sure, it will prevent algorithm to like overfit like this, such that you will get like an approximate algorithm which is more accurate, so that when the new data enters, right? So when the new data enters, it's able to like predict properly. That's basically this parameter, alpha into y minus yi, so that it doesn't overfit. Note that the update above looks identical to the perceptron update of equation 2.2. Yeah, so perceptron has like the same equation than this. The updates are, however, not exactly identical because of how low, no, because how the predicted value yi is computed in the two cases. In the case of perceptron, the sign function is applied to w.xi in order to compute the binary value yi, and therefore the error yi minus yi hat can only be drawn from plus 2. In least square regression, the prediction y hat is real value without application of sign function. This observation naturally leads to the following question: what if we applied? Okay, what is he saying? Perceptron two cases. In case of perceptron, sign function is applied to this. So he's saying again. He's saying in case of perceptron, you're getting like a binary output, right? Binary value of I, and therefore the error can only be drawn from +2 or -2. In least square regression, it is a range real value without the application of sign function. So if you don't apply sign function, the value is real. This observation naturally leads to the following question: what if we applied t-square regression directly to minimize the square distance of the real value prediction from yi from the observed targets belonging to yi, comma this thing? What if we apply here directly to minimize the square distance of real value prediction? The direct application of regression to binary targets referred to as t-square classification. So he's saying, what if we use this model on a binary target, which is either two buckets like classification. I don't know the bucket is still there or not. Yep, right here. Binary target. So it's either 0 or 1. What if we use this on this? Is saying here. The application of least square regression to the binary target is referred to as least square classification. God bless. The gradient descent update is the same as shown in this, which look identical but that of a perceptron. However, the least square method does not yield the same result as perceptron algorithm. This is important because the real value training errors yi comma in is computed different. So the error is basically computed differently. Even though the output is the same, the way the error is computed is differently. So here the error are real values for least square, and here the error are integers for perceptron. And this is a direct application. Least square is referred to as Windroff-Hoff learning, and that's basically like what he's saying. Yeah, this is identical to perceptron, but the way it calculates the error is different from that to perceptron. That's it. That's the video. Damn, I hope you guys like it. Bye.